There's one point I want to make here about some interchange node implications or limitations when we're talking about doing the HPR function. There's a whole history behind this that I'm not going to go into right now. There are probably other presentations on it if you look for them. But the bottom line was this. At an interchange node, which is this node right here, if the interchange node starts a session into the APPN network and all of the links are HPR capable, then we can establish a single RTP pipe that spans the entire session path. However, if part of the session path goes into the subarea network here, the interchange node had some problems with respect to the way that it allocated network addresses and then made sure that the network address didn't have to change as the APPN portion of the route maybe got recomputed when sessions got queued, etc. So the only way we could solve that easily for links over here which actually support, for example, only HPR, like an EE link right here, we can't do ISR routing across it, so what we decided to do was have the interchange node, whenever the session starts in subarea, the interchange node forces the first HPR pipe into the APPN network to be only one hop long. And that would be to the adjacent APPN network node. From there, we could start another HPR pipe that extended the rest of the APPN session path. Unless, of course, there happened to be an interchange node on the far side also, in which case the same one-hop RTP pipe next to the interchange node would also apply. So we can do pure APPN across the APPN portion of the network, but if the session actually hops into subarea, then we're going to get back-to-back pipes typically at the node adjacent to the interchange node. There's one more important note that I would like to make. V1R10 and later interchange nodes, they introduce a coexistence problem with prior releases of VTAM as a result of implementing the HPR seslim function. And you don't have to enable the HPR seslim function on that V1R10 or later interchange node in order for the coexistence problem to actually occur. You can actually get sessions to fail with the infamous 0897000 ABLE sense code. So the only way to avoid this coexistence problem is, one, you can make sure that all the other APPN attached VTAMs in your network and in any APPN attached border node networks, all of them have to be at V1R8 or later. If they're not at V1R8 or later, they have to have a coexistence PTF applied, which brings them up to the V1R8 level. We've got one APART here for V1R7. We've got another one here that was released for V1R6 and V1R4. It's only available to extended service contract customers because they're the only ones who can get maintenance for V1R6 and V1R4. Finally, when we realized what kind of hassle this was going to present to some customers, because not all customers know what level is running on all other customers' VTAMs, we decided to provide another way to get around the coexistence problem. And that is a new function APAR that was shipped on V1R10 and V1R11 and will be in the base of any subsequent releases that come out. This new function APAR provides a new value for the HPR seslim start option called disable, which effectively disables all of the new HPR seslim functions so that it eliminates the coexistence problem completely. So if you can't be sure that all the other APPN attached nodes in your network are at the right level, you can at least make sure that your interchange node is at the right level, and you can disable the HPR seslim function, and that will eliminate any of the coexistence issues that would be out there. All right, now we're going to talk a couple of charts here now on central directory servers. A central directory server is basically a node that's used to minimize broadcast searching in the network. The network topology database defines all network nodes in the network and also defines which nodes are capable of being central directory servers or configured as central directory servers. In the base APPN architecture, all network nodes in the network were required to look in the topology database for a central directory server, and if one was found, the network node would defer the network broadcast search to the central directory server instead of performing that network broadcast himself. If every network node goes to the central directory server can do one broadcast search when the first request comes in, save the information in his directory services database, and then every other network node who comes in looking for that same LU name gets the benefit of the fact that the central directory server already has it cached. So instead of each network node performing a broadcast search for every possible target resource, we've now got it reduced down to one broadcast for each resource from the central directory server, and all the other network nodes can basically take advantage of that. All right. If you have too many central directory servers in your network, it can actually mean too much searching going on. Partly because a primary central directory server will query the alternate central directory servers for information if they don't have anything in their database, or if the information in their database appears to be out of date. So that's one case where central directory servers query each other. But the broadcast search is also going to hit all the central directory servers, and if those central directory servers happen to be interchange nodes as well, then there's a serial interchange node search that comes afterwards that can actually hit all of those central directory servers as well. So you can see now that 3 different searches may actually hit all of these nodes. The more of these nodes you have, potentially the longer this will take for a search to complete, either successfully or in a failure case. So the bottom line is too many central directory servers can mean too much searching, so it's best to try to configure for your size of the network. All right, so I recommend that customers choose the number of central directory servers based on the network size, and by that I mean the number of network nodes in their network. If you have 3 or fewer network nodes, then I just don't think a central directory server is really needed. And that's because, a broadcast search to 2 adjacent nodes is almost as fast as a directed search. If you've got 4 or more network nodes, then I would probably recommend at least 1 central directory server. I would also recommend that you use that first central directory server, you checkpoint his directory services database regularly, and you reload it in when you restart him again, so that now we don't even have to broadcast the first time unless resources have actually moved, since we cached that information and wrote it out to our data set. A second central directory server may also be needed in this 4 network node or more case, just in case the first central directory server happens to go down or is brought down, for maintenance. Now, if you've got 6 or more network nodes, then I would probably recommend at least 2 central directory servers. If you ever have more than 4 central directory servers, you probably have too many. I'm not sure that I recommend them, but there still might be cases where you want to do that. For example, if you have 4 different data centers, you may actually want a central directory server in each of the data centers to prevent central directory server queries from crossing the country and coming back again, for example. All right. Now, I just talked about putting central directory servers into 2 different data centers, and what you find now is that if everybody's mesh connected using EE, they all look like all the central directory servers look like they're 1 hop away from this network node, regardless of whether they're in the same side of the country or whether they're on the opposite side of the country. So I've developed a little way here, a summary of a way, that you can actually get local network nodes, for example, to use the central directory server that's in their data center rather than going across the country and back. And yet, if their central directory server happens to be down, they can still use the central directory server on the other side of the country as a backup. And the way that you would do that is by changing the weight value for the CP Service Manager class of service only. You change the weight value on the links that you use to get across the country and back. So that would be just these 4 in the middle, the one at the top and bottom and the 2 that cross in the middle. If you change the CP Service Manager weight on those links to make it look like a weight of 60, and you leave the CP Service Manager weight for all the links within a data center, resolving to a weight of 30, then now every time I look for a central directory server, if the one in my data center happens to be closest, then that will be the least weight route, and that will typically be the central directory server that I would use for my search. If that central directory server happens to be down, then the next central directory server is this one over here. It's a slightly higher weight, but it's still the best weight at this point, and so we'll go ahead and use that one.